So today we're going to be looking for the velocity or the differential equation for a rapidly falling object. So we're going to kind of try to figure out what that would look like. So first thing we're going to start off with is a nice little F equals ma. And the reason I do that is that it's always nice to just start off with an F equals ma, because you can now rewrite the F here as and just remember, because this is going to be important in figuring out the acceleration due to gravity, and this also helps us know that acceleration is the second derivative of velocity, of position. So this is sometimes written as F is equal to m dv over dt, right? So that right over there is equal to our force. So now the velocity for something that is falling is going to be typically look like something like this. So the total forces of a free falling object is going to be mg, and remember, g is the acceleration due to gravity. That's how you got to differentiate. It's okay to write this as g, because the normal acceleration in your equation, it's going to be written as dv over dt. So for a falling object, so it's going to have mg, right? That's the force. So let's just consider mg a positive force. So down is positive, and pushing against this is going to be our drag force. So that looks something like, so we're going to do mg minus, and then that's going to be and this is just the drag coefficient times velocity, right? That's what it's supposed to be. But if you remember that for a rapidly falling object, it's a little bit of an exponential growth. So this is going to be, this is actually a quadratic. So if it's falling at a linear rate, then it's okay to just not square this, but because it's rapidly falling, then we have to square this. And then now we got to kind of dig into this. So let's set the left side equal to m dv over dt, and this is equal to mg minus the drag coefficient times velocity squared. Now let's divide both sides by m so we can actually get this in a differential format. dt is equal to mg over m minus the drag coefficient, velocity squared, all over. This looks like a y. I'm just not very good at writing the drag coefficient, or the symbol for it, divided by m as well. Okay, so that's what we're looking at right now. So we know that this is going to cancel out, this is going to cancel out, and we're going to be left with, so dv over dt is equal to g minus the drag coefficient over m multiplied by velocity squared. Okay, so this is what we're looking at right now. Now, if we wanted to know what would be the terminal velocity, and remember, the terminal velocity is the velocity that is going to be at equilibrium, right? So after the drag has canceled out the gravity, the acceleration due to gravity, what's the velocity with which the object is falling down? And so this is what we're going to get over here. So let's just solve for it. So we're going to have to set the rate of change in velocity equal to 0, because that's the acceleration. So when it's not accelerating anymore, what's the speed that it's falling at? So let's take a look at this over here. Not very good at writing the d here. G m v squared, and then we're going to set the left side equal to 0 is equal to g minus mv squared. Now let's just add this to the left side. Okay, so we're going to get v squared is equal to g. And we're going to multiply both sides by m, so we're going to be left with the drag coefficient velocity squared is equal to the acceleration due to gravity times m, and then divide both sides by the the drag coefficient. So we get velocity squared is equal to the acceleration due to gravity times mass, all divided by the drag coefficient. Let's continue over here. Just draw a little line. Say we're continuing, and then let's continue. So this is going to equal that. There's only one step left. So the terminal velocity, right? So velocity, all right, t. So the terminal velocity is equal to the square root of the acceleration due to gravity times mass all over the drag coefficient. So there we go. That's what we have so far. Okay? And that's where we're going to end this for now.